Let's welcome our next presenter, who is Younghyun. The stage is yours.
Hi, thank you very much. I'm Younghyun Oh, PhD candidate in Sungkyunkwan University. I'd like to begin with thanking the organizing committee for giving me this opportunity to share my work. So let's begin. And I have no disclosures. This is the brief overview of my study. We're going to start with the theoretical foundation, and then I'm going to introduce the methodology that I've used to investigate the theory, and then show the validation of the theory using my method. So first, the theory. My work is based on this paper by Passingham et al. 2002. The paper name is The Anatomical Basis of Functional Localization in the Cortex. There were two key propositions made. One is, each cortical area has a unique pattern of anatomical connections, known as connectivity fingerprint. And second is, these fingerprints constrain the functional specialization of regions, leading to a hypothesis that a region's functional role is determined primarily by its unique pattern of interregional connectivity. In our previous study, we developed a unique way of integrating effective connectivity methods to make a unified one. If you're interested in, you can scan this QR code to read our preprint. In this talk, I'm going to give a brief overview of my EC framework. So the principle of our IEC method is that we utilize the fact that EC algorithms capture different aspects of directed interactions. For instance, we found that there is a theory-driven categorization of EC methods. For instance, you can see that the biggest category is graphical models versus dynamical systems. Using resting state fMRI data, we empirically validated these categories. Then we devised a Bayesian optimization technique to integrate it to make a unified one, which we call IEC, which is a single weighted and directed network capturing intrinsic connectivity. In our preprint, we went through a rigorous validation using macaque fMRI, simulation, and human fMRI. But for the sake of time, in this talk, I'm going to show you briefly the validation of IEC using human fMRI. So we basically inferred the EC results from individual algorithms using HCP dataset, and then made a IEC in the testing dataset using the optimal beta values that we found in the training dataset. Then we used this IEC matrix as a long-range scaffold in our Hof simulation model, and then compared the simulated FC and FCD to their empirical counterparts. And the performance was pretty great. In terms of static FC, the R value was 0.81. Also, in terms of the dynamic FC, the KS distance was 0.13. And the simulated Bolt signal also additionally captured the intrinsic time delay structure of the empirical fMRI. Moving on, so we have the connectivity matrix. To infer the functional specialization, we used the multi-domain task battery dataset by King et al. 2019, which includes more than 20 task conditions, each eliciting a unique brain activation patterns. Specifically to measure the functional specialization, we borrowed a concept from electrophysiology known as neural population coding. My collaborator, Taku, did a really nice work showing that this concept can be generalized to the neuroimaging, especially at the parcel level. So basically what we did here is we measured the mean activation pattern of each brain area for different task conditions. For instance, in this matrix, each row represents the unique activation patterns of that brain region for 25 different task conditions. Then we correlated these activity patterns of each brain area and called it signal correlation because it measures the correlation of brain activity patterns. Then we constructed the IEC metrics using independent HCP dataset, then compared the connection similarity of any pair of two brain regions in terms of their outgoing connections, leading to a question whether the pattern of connectivity, i.e. the connectivity fingerprint, can explain the pattern of task activation patterns. So this is the result. We can clearly see it is very similar, showing a modular structure according to 7 functional networks. More quantitatively, the connectivity fingerprint metrics captured a large variance of signal correlation matrix with the R-square value of 0.47, which was the highest compared to the raw EC metrics, FC, and the connectivity fingerprint of FC, which was very interesting because connectivity fingerprint of EC showed the highest, while the connectivity fingerprint of the FC showed even lower R-square value compared to the FC. So far, we showed that the connectivity fingerprint, the idea of it, can capture the regional tuning, but how about the large-scale functional organization? To do that, we projected the 2 matrices into the low-dimension structure using multidimensional scaling. And this is the result. Each circle represents a brain region color-coded by their affiliation to the 22 modules in the MMP parcellation. We can see that IEC fingerprint captures the differentiation between sensory and auditory and visual, but somehow signal correlation agglomerates the auditory and sensory. And then in terms of more quantitative network characteristics, the IEC fingerprint captured the segregation and modularity like best even compared to the signal correlation matrix. So we showed that connectivity fingerprint can capture the regional tuning and also modular organization of the brain, but how about the hierarchy? So one thing about the hierarchy in the brain in terms of function is there is a function receptive field across the brain hierarchy, and we try to capture it using the distribution of connection similarity value. For instance, what's shown in this cortical map is the connection similarity value or the fingerprint similarity value between V1 and every other brain regions. And we see that the V1 shows a high similarity value within only the visual cortices, resulting in high cortices value. Compared to this, the area 32, part of the frontal area, shows a lower cortices value, showing a high distributed high similarity across many brain regions. And this is the cortices map, showing a very unique pattern where visual, sensory, and auditory areas have high cortices value, while heteromodal areas show comparatively low cortices values. So we compared this to cortical type information, which is implicated in the anatomical hierarchy, demarcating each cortical region based on the laminar specificity. And nicely, the cortices value decreased along the anatomical hierarchy, maybe indicating that there is some interaction between structure and function in shaping the function receptive field, and maybe indicating that our connectivity fingerprint can capture the function receptive field across the cortical hierarchy. To wrap up, we revisited the classical hypothesis that a brain region's role emerges from its connectivity embedding, and we used IEC framework integrating diverse EC algorithms, and the connectivity fingerprint derived from IEC predicted functional tuning, network topology, and receptive field structure. With that, I would like to thank my collaborator, Takuya Ito, and my supervisor, Seokjun Hong, my lab members, and last but not least, my funding sources, without which this work could not have been done. And if you're interested in further, you can come to my poster or email me. And also, if you're interested in the IEC framework, you can scan this QR code to read more about, and thank you for your attention.
Thank you for this very good overview. So we do have a question in the audience that got a lot of upvotes, and it is, why do you think that the IEC fingerprint captures modularity better than the signal correlation matrix?
Yeah, that's a really great question. I think I would like to borrow the concept that Victor just brought up, where he said the intrinsic brain geometry and structure shapes the manifold of the brain activity, and then intrinsic connectivity, or intrinsic effective connectivity sample from resting state evenly sample the manifold. But the signal correlation matrix may be oversample some task over the others, and especially in the MDTB data set, it overly samples the visual tasks. So maybe that's why it can segregate the visual areas while not segregating the auditory from the sensory. I guess that makes sense.
Yeah, thank you. Any other questions from the audience?
That was a lovely talk. I really like the method. You know my question. Have you thought about looking at the subcortex, and do you have any interest in speculating what you think we'd see when we look there? Because the bold signal can often look quite different in the subcortex.
Well, obviously, yes, I've been thinking about subcortical structure, but there was one problem in estimating effective connectivity between subcortical cortical structures. For instance, thalamus has a very widespread diffusive connections, and cortical connections have very unique interregional connections based on like pyramidal neurons. And then if we estimate effective connectivity between thalamus and cortex, say in the same way that we estimate the cortical connections, it, I think, violates the assumption that thalamus-cortical connections uniquely have. I think for that reason, we need to work on like more technical advancements in estimating effective connectivity from thalamus to cortex and vice versa. And if we have that, then I would love to see how it interplays with the finding that I have. Thank you.
Thank you. Let's thank the speaker again.